This flip lesson will be on turning forces. The main objectives of this flip lesson will be to be able to describe what is meant by turning force and to be able to calculate the moment of a force. Take a moment now to highlight the key words that are in these objectives. The main keywords that we'll be looking at in this flip lesson are listed at the moment. Some of these you may have seen before, and some of them you may actually be able to exactly relate to what they mean during the rest of this lesson. To help you understand moments and also turning forces in a bit more detail, it's important to go back to the basics. So, a basic example, whenever you open a door, you are using a turning force, which you can see through my nice little picture of a door handle. I want you to pause the video here and to list as many other different turning forces that you can think of. A turning force acts at a certain point from a pivot. And to understand what a pivot is, you need to know that it's a point at which a lever or a seesaw potentially could balance. And so in the image below of the seesaw, the pivot in this case will be the centre. This is the location at which our seesaw could balance based on a number of factors. For example, the force and also the distance, and that is something that we'll come to later on. Another key point in order to understand turning forces is we need to be able to define the term moment and how it applies in this calculation and also in this topic. And so a moment is the actual turning effect of a force, and this is a moment. So a moment defined would be a measure of the ability of a force to be able to rotate an object about a pivot. And so if we go back to my image of these two little kids playing on the seesaw, and we actually apply what a moment means, it can therefore be the ability of a force to rotate around our pivot. Therefore, our actual calculation would be how much force each of them are applying. So this would be our downwards force, and also the distance they are from our central pivot. Therefore, the actual calculation, how to work a moment out, would be moment equals force times perpendicular distance from the pivot. As always, you should know that the force will be measured in newtons, and typical science, our distance will be therefore measured in newtons. If our newtons are being timed by meters, our moment's unit of measurement will therefore be Newton meters. So now you know a little bit more about the actual calculation used and the different units of measurement that we use to calculate what a moment actually is. we can start talking about the law of moments. So, if we look at our picture one more time of the two playing on the seesaw, the person on the left hand of the diagram, their moment will be working in an anti-clockwise direction. The person on the right, their moment will be working, if you can have already guessed it, in a clockwise direction. All based, remember, around our central pivot point. And so, if we have a moment that is in equilibrium, meaning that our moment could be balanced, the sum of the clockwise moment will therefore have to equal the sum of our anti-clockwise moment. So let's actually put this law of moments concept into action and work out and use a worked example. Okay, so here is some figures that we can actually put into place and use our equation of how to work out a moment and put it into practice. So if we start on, actually let me just go through these figures with you. So on the left hand side we can see that the force acting downwards would be 500 newtons. And the person on the left is sitting 1 meters away from our central pivot point. Similarly, on our right hand side, the force acting downwards will be it could be 1000 newtons. However, he is only sitting 0.5 meters from our central pivot. Now let's remind ourselves of our moment calculation at the top of this slide. So a moment equals a force times perpendicular distance from the pivot. So let's start with the person on the left, who will therefore be, if you remember from before, our anti-clockwise moment. So his force is 500 newtons and his perpendicular distance from our pivot is 1 meter. Therefore, that moment will be 500 Newton meters. Now let's look at our clockwise moment, the person sitting on the right hand side of the seesaw. Our our force will be 1000 newtons times by our perpendicular distance from the pivot, which is 0.5 meters. Therefore, our answer will be 500 Newton meters. 1000 times 0.5, half of 1000 is 500. So as you can see, our moments from both our clockwise and our anti-clockwise are both the same. Therefore, the seesaw will balance, and this is going back to our equilibrium and our law of moments. So I'm now going to give you a question on the next slide, which you should pause, work it out for yourself please, and then see if the moments balance, and if not, which direction will the force be the greatest in, and our moment will be the greatest in. So an answer could potentially end up as 250 Newton meters to the left or 250 Newton meters to the right, depending on which one has more. Here is your question. Work out the moment of each side of the seesaw, so our clockwise and our anti-clockwise moment, and then work out the overall moment. The person on the left, so that will be our anti-clockwise moment, has a force of 750 newtons, and is at a perpendicular distance of 2 meters from our central pivot. The person on the right is working in a clockwise moment and has a force of 330 newtons and is sitting at a distance of 1.75 meters from our central pivot. Pause this video now and work out the question and work out the answer. And now, if you haven't already had enough of moments or hearing my voice, here are 2 more questions for you to practice your newfound skills of moment calculations on. Pause this video here and work out the answers. And now for your final task, it is to design a balancing game that children can play. Explain in terms of the law of moments how they can play it. So take everything that you've learnt from this flip lesson on pivots, turning forces, the law of moments, and also the actual calculation, how we can work out moments in order to design this little game. Have fun. It is what it is worth 6 marks, so include as much detail and explanation as you possibly can. Remember our command words in this question, obviously design, so you're designing a game, and your explanation. So it's not just description of what they have to do, it's more what they can do and much more of the explanation. So how does the law of moments help them play it? And this will be due in on Wednesday, along with all of the answers you've previously worked out, and that will act as our starter activity on Wednesday. Thanks. Bye.